Okay, so now that we know all about water and hydrogen bonding and dissolution, let's talk about what makes certain compounds acidic or basic. So let's first start off with oxides and hydroxides. Oxides and hydroxides. And the reason I'm grouping them together is because they are related in the sense that if we have some sort of element hydroxide, which I'll draw in green, so E, just any element in the periodic table, and then we add water to it, you could then have a balanced reaction in which we have maybe EOH2. So any oxide can be transformed into the corresponding hydroxide through that balancing. And of course, O could be a different, like maybe we could have ON here. And then so in this case, it wouldn't be 2. It would be a certain number of waters. And then we have maybe greater than 2 in the final product. So I'll just kind of put like maybe M. Something like that, as long as you're stoichiometrically balanced. So what makes them acidic or basic? And then, so that has to do with electronegativity. So the basic idea is that if we have our element hydroxide, so which could come from an oxide, so here is EOH. So if our element has a low chi, then what happens is, then if we have our overall, we'll have a big delta plus and a big delta minus between this element and oxygen. So big delta plus, big delta minus. And then as a result, our kind of positive charge here is maybe smaller. So this is the biggest difference in electronegativity between our low chi elements and then oxygen. So for example, if we have, let's say, sodium hydroxide, then of course our biggest polarity difference is between sodium and oxygen. And then so as a result, when water comes in, so here's my water molecule as we put it in solution. So water's going to try to come in and associate with the biggest positive charge. So here we could have it going to this oxygen, and then we could also have water coming here into this element. So then as a result, what ends up happening is that we're going to break this OH bond, and then so this will be our kind of basic scenario. So we could have something like our element hydroxide could then release and become our aqueous ion plus OH minus. So releasing hydroxide would be Bronsted basic. We could also have it react with the proton. That's also the same thing as being a base. And then we get to so these are our kind of basic scenarios. So if you have a very low electronegativity element, then your overall metal oxide or metal hydroxide is going to be basic. And also it's going to be because the metal oxide itself is very ionic because we have our different positive charges. So this will be kind of like sodium oxide, for example, would be an ionic kind of 3D salt type structure. Okay. As we go further across the periodic table, if we go very, very far to the right, if we have, let's say, a high electronegativity, then what's going to happen is then as we form our element hydroxide, then if this is high electronegativity, our delta positive between here and here is going to be small. So this will be small delta positive, like because these are very close together. So the biggest difference between electronegativity between oxygen and the proton. So this will be our biggest delta plus, and then here's our delta minus. So again, this difference is going to be greater than this difference here. And so therefore, when water comes in, our delta minus on the water is going to want to go to the proton rather than to the E element. And then we'll still have our kind of proton here. And then so as a result, we're going to be splitting this OH bond rather than the EO bond. And then so for acidic, conditions, we could have our element hydroxide. So this is kind of like a misleading term. It's a hydroxide, but it's going to react as an acid. So then, in this case, it could either lose a proton, or it could react with a base, right? So if it reacts with hydroxide, that's removing hydroxide from solution, so it's acting as an acid. And then so you could have something like N+1, and then overall, this will be minus charged. So as an example, we had sodium hydroxide here. For example, here, we could maybe have, let's say, I'll go up here, like CO2, for example. So this is the oxide of carbon dioxide. If you add water to it, this forms H2CO3, carbonic acid, so that's acidic. Okay, so that's high electronegativity. So these are kind of like the two opposite ends. If we have our very low electronegativity, or basic ionic, over here, CO2, of course, is covalent molecular. So that just has to do with kind of what we were talking about before with electronegativity differences. And then so in water, this is acidic. Of course, as we go kind of in between, you could have maybe our covalent polymeric species where our electronegativity is kind of in the middle. And then so those could be what's called amphoteric. So I'll put this in the middle. So amphoteric. Amphoteric, meaning that it can act as both an acid or a base. And so if you remember from your periodic table from high school, we have like the metal, non-metal, metalloids. So maybe the metalloids would be more amphoteric. And so as an example, carbon dioxide is acidic in water, but as we go further down, silicon and then germanium, they are more amphoteric because we're getting closer and closer to kind of metal behavior. On the very far end, if we have something like tin oxide in water, this is basic because we've got electronegativity is much, much lower for tin. Okay, so that's all I wanted to say about oxides and hydroxides.